Maybe. Okay, so 3-2, we are looking at graphing polynomial functions. You looked at this last year. So the thing about polynomial functions, a parabola is an example of one. Okay, but now we're going to look at higher order, so higher degree. So we have our definition of a polynomial function. One of the things we're going to look at the most is a sub n, which is just the coefficient of the variable to the highest power, or the leading coefficient. Okay, that's going to determine the shape of our graph. Okay. One of the things about a polynomial function, which we see with our parabolas, is that they're continuous. So if you look at this first picture, we have our continuous smooth graph. There are no jumps. There are no pointy parts. Okay, versus the non-polynomial functions, we have a jump in our graph, or we have a sharp corner. Okay, which this would be a piecewise function. Actually, both of them would be. Okay, so we're looking at continuous polynomial functions. So the first thing we're going to look at is the end behavior. So what's happening to our graph on the where the arrows are. So the behavior of the graph of a function to the far left or the far right is called its end behavior. Although the graph of a polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound as it moves far to the left or far to the right. The end behavior of a polynomial function depends upon the leading term, and so that includes the leading coefficient and the degree. So for n is odd, okay, so we have a sub n, remember that means our leading coefficient. Okay, so our leading coefficient. So if our leading coefficient is positive, okay, with an odd degree, that means that we have something that looks like it has like a positive slope. So it starts on the left, it's falling, and on the right, it's rising. Okay, so another way you'll see that falls to the left, rises to the right. Falls to the left, rises to the right. So if a sub n, or that leading coefficient, is now negative, the slope changes. So now we are going up on the left and down on the right. So it rises to the left, falls to the right. I'm okay if you just use the arrows to talk about the end behavior on some of your homework. It's going to actually have those words, falls and rises. So easiest way to remember odd, I'm going to slide this over a little bit. Okay, so our lowest odd number is 1. Do you agree? Okay, so think about that. It's a line. It's like y equals mx plus b. So our leading coefficient would be that slope. Okay, so when m is positive, our line is going up from left to right. And if m is negative, it's falling. Okay, so it's an easy way to remember your odd degrees. The only difference is going to be is that you're going to have like a space in between these where we don't know what's happening between the arrows. Okay, and we'll talk about what that looks like on the next page. Okay. Okay, so if n is even, okay, if n is even, if our leading coefficient is positive, our end behavior is up, up. And so we're going to say rises to the left and right. And then if our leading coefficient is negative, we have down, down. So it falls to the left and the right. Okay. So our lowest even degree is 2. which is the graph of what? You can talk. Degree 2. This is what we just did in 3-1. What were the graphs? Parabolas. Okay. So y equals x squared. So if a, so if I put an a in front of there, y equals ax squared. If a is positive, this is good for your quiz, which way is your graph facing? Up. Okay. So both the end behaviors are up. And if a is negative, your graph is facing down. Okay, which matches the end behavior definitions. Okay. So use what you know about a line and a parabola to help you remember those end behaviors. Okay. Questions with that? All right. Next page. Okay, so applying that to a polynomial. So use the leading coefficient test to determine the end behavior of the graph of these two functions. So our first one, f of x equals x cubed plus 3x squared minus x minus 3. So we have two things we want to look for. The degree, and I'm going to just say, what's here? And our leading coefficient. I'll write it out. Leading coefficient is the number in front. And the degree is your highest exponent. So what's your highest exponent? 3. Is that even or odd? Odd. And our leading coefficient, what's the number in front of x cubed? 1. Positive or negative? Positive. Okay. So if it's odd, we know they're going opposite directions. Now the question is, are we falling and then rising, or are we rising and then falling? Falling and then rising. So down, up. I'm okay with you just putting those arrows to represent what's happening. Okay. Okay. Looking at the next one. So again, degree and leading coefficient. And I'm just going to abbreviate LC. So I want to write it out again. Okay, so this one's going to be slightly different. So this one's factored already. Okay, so you kind of have to do some multiplying / adding. Okay, so what is our degree of this little part? 3. Here? And here? Add those up. 3 plus 2 plus 1? 6. So that is your degree. Okay. So you can multiply this whole thing out, but that's going to be a whole bunch of work. Instead, just add up your exponents. So we did 3 plus 2 plus 1, and we got that 1 because there was no exponent on the last binomial. Okay, so is that even or odd? Even. So automatically we know what about our end behavior? They're going to go the same direction. They're both going to go up or they're both going to go down. So what's our leading coefficient? -4. So we're looking at the very front, which is obviously negative. So what's our end behavior going to do? Down, down. Okay. So that's what we're going to use to help us graph our functions. Okay. The other thing we're going to use is the zeros of the polynomial function. We looked at this when we looked at parabolas. Zeros are the same thing as x-intercepts. Zeros are the same thing as x-intercepts. So in order to find an x-intercept, remember we set our function equal to 0, and then factor. These you will be able to factor. Okay. So for the first one, f of x equals x cubed plus 3x squared minus x minus 3. When there's 4 terms, how do we factor? Grouping. So I'm going to set it equal to 0. And then we're going to group the first 2 and group the last 2. So x cubed plus 3x squared, what's their greatest common factor? x squared. X cubed divided by x squared. X plus 3. Then negative x minus 3, what's the GCF? Negative 1. And what are you left with? X plus 3. Our parentheses match, so we can move on. So we have the quantity of x plus 3 times the quantity x squared minus 1. But x squared minus 1 can factor further. Anybody remember how? Difference of two squares. What's the square root of x squared? What's the square root of 1? So plus 1 minus 1. Okay, so that's your factored form, which is what we're going to be using, okay, here in a bit on the next page. But if we want to go ahead and figure out what does x equal, so if x plus 3, what would x equal? Negative 3. X plus 1, x would equal? Negative 1. And x minus 1, x equals 1. So these are our x-intercepts, or our zeros of our function. Okay. So same thing we did when we were solving for our x-intercepts, we just have more than 2. Okay, look at the next one. F of x equals negative x to the 4th plus 4x cubed minus 4x squared. We have 3 terms, so check for a GCF. Is there a greatest common factor? X squared. And also, since we start off with that negative, I'm going to say our GCF is a negative x squared. Okay, so it's negative x to the 4th divided by negative x squared. X squared. 4x cubed divided by negative x squared. 4 divided by negative? Negative 4x. And negative 4x squared divided by negative x squared. Plus 4. Okay, when we have 3 terms, we just factor AC. Here A is 1. So we just really need to look at our last value of 4. So what multiplies to be 4 and adds to be negative 4? Negative 2, negative 2. What's another way we could write that? X minus 2 squared. Okay. So if negative x squared equals 0, what does x equal? 0. And x minus 2? 2. Okay. Here's the thing about polynomial functions. You should have the same number of zeros, or x-intercepts, as you do as the highest order. Okay. So if we look at this top one, our highest degree was what? And how many x-intercepts did we have? 3. Here, what's our highest order? But how many x-intercepts did we have? 2. But this was squared, right? So this could also be rewritten as negative x times x minus 2, x minus 2. Do we agree? So if we look at it that way, that would give us 0, 0, 2, and 2. Yay, nay? Okay. So how many x-intercepts did we have? 4. You just don't necessarily need to rewrite them, okay? So that idea of having the same number of x equals as your highest degree, that's going to come into play on Monday's notes, okay? But I wanted to point that out for our graphing, okay? Okay, so we kind of just talked about this next first part. So, multiplicities of zeros. We can use the results of factoring to express a polynomial as a product of factors. Okay, so that's what we just did here and here, or this one, whichever one you want to look at, okay? And where you're multiplying, you haven't actually solved for x, so factored form, okay? So, for instance, on the previous example, we can use our factoring to express the function's equation as we had negative x squared times the quantity x minus 2 squared. Okay, notice that each factor occurs twice. So in factoring equation for the polynomial function f, if the same factor x minus r occurs k times, but not k plus 1 times, we call r a 0 with multiplicity k. So all that's saying is how many times does that 0 occur? So for the polynomial function above, we said the zeros, x equaled 0 and x equaled 2. Agree? Yay, nay? Okay. So now the multiplicity of that 0, so how many times did 0 occur? Twice. So the multiplicity is 2. What about when x equaled 2? What was the multiplicity? Also 2. Okay, so that's all that's saying is how often is it occurring? So based off that, that tells us what happens at the x-axis. So multiplicity provides another connection between zeros and the graphs. The multiplicity of a 0 tells us whether the graph of a polynomial function touches the x-axis at the 0 and turns around, or if the graph crosses the x-axis at the 0. So if r is an even multiplicity, the graph touches the x-axis and bounces back. Okay? Think about it like a parabola. Okay? So as you get to the x-axis, that's your x value, and its multiplicity even, it's going to look like a parabola. It's going to touch the x-intercept and then bounce back. Okay? For odd multiplicity, also need to make sure you know that, it's going to cross the x-axis. So if that's r. So if this is our point for r, it's going to cross through it like a line would. Okay, so still use that idea of odd as a line, even as a parabola to help you remember those rules. Okay. To abbreviate, rather than having to write touches and bounce back, I'm okay if you just abbreviate this bounces back, BB, and then for crosses, CT, crosses through. Okay. Under homework, it's going to say touches. Bless you. Okay. That's the same idea. Touches and doesn't go through. So if we look at this example, they're already factored for us. Find the zeros of f of x equals 1/2 times the quantity x plus 3 times the quantity 2x minus 3 squared. Give the multiplicity of each 0 and state whether it crosses or bounces back. Okay. So for our zeros, okay, 1/2 is just our leading coefficient. What about x plus 1? What would that 0 be? -1. So x equals -1. How many times does that 0 occur? Once. Okay, if you need to, put a 1 here on the outside of the parentheses. So our multiplicity is 1. So is that going to cross through or bounce back? Cross through. So I'm just going to put CT. So on a quiz or test, I'm okay with you just writing that. Okay, looking at the next set of parentheses. 2x minus 3 squared. What would x equal? Add the 3, divide by 2. So 3/2. Or 1.5, however you want to think about it. What would the multiplicity be? What's the highest degree on it? 2. So is it going to cross through or bounce back? Bounce back. Questions? Okay. For the zeros, f of x equals -4 times the quantity x plus 1/2 squared times the quantity x minus 5 cubed. Okay, so for your zeros, what does x equal for the first one? -1/2. What's the multiplicity? BB, bounce back. And this next one, x minus 5 cubed. What's the 0? 5. Multiplicity? 3. Nope, you're good. And then bounce back or cross through? Cross through. Okay with that? Alright. The next part is just kind of a test. Okay, it's called the intermediate value theorem. And it says let f be a polynomial function with real coefficients. If f of a and f of b have opposite signs, then there is at least one value of c between a and b for which f of c equals 0. So here's what that says. If you have two numbers, so let's say 2 and 3, and you plug them into your function and you get opposite signs. So one's positive and one's negative. Okay. That means if like this is your x-axis, you have a positive one and a negative one, right? Wouldn't it have to go through the x-axis? Which means you have some type of x-intercept, okay, or a 0. So that's all that's saying. So it's more like a test to prove something. So if we do this one, show that the polynomial function f of x equals x cubed minus 2x minus 5 has a real 0 between 2 and 3. So we're going to find f of 2, and then we're going to find f of 3. And see if we get a positive value and a negative value. If they're both positive, then we don't know that there's 0. So, plug in 2. We have 2 cubed minus 2 times 2 minus 5. So what is 2 cubed? 8. Minus 2 times 2? And minus 5. So what's 8 minus 4? 4. And then 4 minus 5? -1. Okay. So if you need to, think of it as now you have the ordered pair 2, -1. If I sketch like a little graph here, we have that point. Okay, so now f of 3. So 3 cubed minus 2 times 3 minus 5. What is 3 cubed? 27. Minus 2 times 3. And then minus 5. 27 minus 6. Minus 5. 16. So we have the ordered pair 3, 16. So if we go over to 3, and that would be somewhere way up here at 16. So if you were to connect those for your polynomial function, does it cross through the x-axis? Yeah, so that's the intermediate value theorem. We don't know what that x-intercept is. It's some decimal in between 2 and 3. That's all we know. Does that make sense? Okay. That is more of just a test for what you're going to be doing for graphing, and you'll be able to find all your x-intercepts. So you'll have a couple of questions like that on your homework. Okay, turning points of polynomial functions. The graph changes directions from increasing to decreasing or vice versa. It's called a turning point. If f is a polynomial of degree n, then it has at most n minus 1 turning points. Just a fact. Okay, your strategy for graphing. So first thing, we use the leading coefficient. So remember, this is when we use the degree and the leading coefficient to determine if it's up, 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 down, 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 up. Okay, so looking at those arrows. Then you're going to find the x-intercepts and then use that to determine the multiplicity and then what's happening at the x-axis. Is it touching and bouncing back, or is it crossing through? Okay. the larger the multiplicity, the flatter it is. Okay, so that'll help you with something on one of the questions on your homework. Okay. The one thing we didn't do so far in our notes is find the y-intercept. Okay, all we're doing is plugging in 0 and simplifying. A lot of times, if in standard form, remember it'll just be the constant. So like when we looked at our parabolas, the y-intercept was just c. Okay. So same idea there. If it's in factored form, you'll have to actually solve. Another idea that will help you graph is symmetry. Okay, so remember if your book talks about the y-axis and the origin. Okay, remember if it's all your exponents are even, it's symmetric across the y-axis. If all of your exponents are odd, then it's symmetric across the origin. If it's even and odd, it's neither. Okay, that's another way to check your graph. We'll see an example like that on the next page. And then the last fact is basically just put it all together. Okay, all right, so let's finish this up. Okay, so without the use of a graphing calculator, graph f of x equals x to the fourth minus 2x squared plus 1. So first thing, what is our degree? 4. And what is our leading coefficient? 1. Okay, so we have even and positive. So what's our end behavior? Up, up. Up, up. So since it's even, we know they're both facing the same direction. And since it's positive, they're both going up. Okay, so second, we want to find our x-intercepts. So we have 0 equals x to the fourth minus 2x squared plus 1. Okay, so here we're going to factor with a higher degree. Okay, so normally this says x squared, right? And we would do x and x. If this is x to the fourth, they would both have to be x squared. So 0 equals, so we have x squared, and we leave a blank, x squared. So what are your factors of 1 that add to be negative 2? Negative 1 and negative 1. But x squared minus 1, how can that factor? X plus 1, x minus 1. This one can also factor the same way, x plus 1, x minus 1. Okay. So if you want, you can rewrite this. 0 equals x plus 1 quantity squared, x minus 1 quantity squared. I don't care which way you write it. Okay, so our zeros. So if x plus 1 is in parentheses, what does x equal? Negative 1. What's the multiplicity? How often does that occur? Twice. So is it going to cross through or bounce back on our graph? Bounce back. Okay. Looking at our second parentheses, x minus 1. What does x equal? 1. That multiplicity is also 2. And it's going to also bounce back. Third thing we want to find is our y-intercept. So find f of 0. So we have 0 to the fourth minus 2 times 0 squared plus 1. which leaves us what? 1. Bless you. And then symmetry. Looking back at your original, looking at your exponents, are they all even or are they all odd? Even. Which means it's going to be symmetric across the y-axis. Symmetric across the y-axis. Okay, so we have everything we need to graph. Okay. So since our zeros are -1 and 1, I'm going to expand our graph. So let's go by, like, let's see here, like by quarters. So every 4 spots, let's say that's 1. Okay. That way it's not so scrunched up and we can't see what's happening. So go 4, -1, and then another 4 gives us -2. If you had something like this on your quiz or your test, I'm okay with you not increasing your scale. We're just doing it for notes so we can see what's happening. Okay? Okay, so start off with your x-intercepts. Okay? So this is what you're always going to graph first. And then graph second. Okay. So we have an x-intercept at, -1. And an x-intercept at +1. And then we have a y-intercept at +1. So you've plotted your points. Okay. And now you're going to use your end behavior. So on the left-hand side, are we going to start at the top or the bottom? The top. Okay. So we're going to come up here, we're going to start at the top, and we're going to go towards that x-intercept. When we get to that x-intercept, are we going to touch it and cross through it, or are we going to touch it and bounce back? Bounce back. So we're going to come back up. Okay. We don't know how high we need to go, but we know we need to go through that y-intercept. So we're going to go up and go through it. And then we know we need to bounce or come back down to this x-intercept. So we're going to come back down. When we get to this x-intercept, do we cross through it or do we bounce back? Bounce back. Okay, so now check. Our in behavior said that we should be up, up. Are you up, up? Okay, so that checks out. The other thing we can check is our symmetry. Based off our exponents, we know we're symmetric across the y-axis. It's a sketch, but is it for the most part the same on both sides? Yes. So that's your graph. Questions? Okay. What if I asked you your domain? Negative infinity to positive infinity. That will always be true for polynomial functions. What about your range? What's your bottommost y value? 0. Okay. Another thing you can see with polynomial function is increasing, decreasing, and constant. Okay. Okay, so when is our graph? So let's see here. From the start to our x-intercept, what is your graph doing? Decreasing. So we can say from negative infinity, remember increasing, decreasing, constant is always using your x values. So what's your x value in which it changes direction? -1. Okay. Then from -1 until 0, it is increasing. At 0, it switches to start doing what? Decreasing. From 0 until what? So 1. And then from 1 to infinity, it does increasing. So what does your graph never do? It's never constant. No, so we don't put brackets because at this point where it changes direction, it's neither increasing or decreasing. It's our minimum or our maximum value. Okay? So yeah, you could say you have two minimum values at -1 and 1. What would that minimum value be? It's a good review. So it's at the x value. What's the y value? 0. Okay, so same thing with your parabolas. Okay, it's at the x. It is the y. Okay, what would your maximum be? Where's it at? 0. And what is it? 1. Okay. All right. Last one. F of x equals -2 times the quantity x minus 1 squared plus the quantity x plus 2. What's nice about this is it's already factored for us. Okay? So first thing, we need to find the degree. Careful about this one. Remember, we have to add it up. So how many times does this one occur? Twice. This one, which adds up to be 3. Leading coefficient is -2. So we have an odd degree of 3 and a negative leading coefficient. So what's your graph doing? It's up, down. Okay, so remember, if it's odd, it's like a line. So it's either going like falling or rising, like the slope, right? Okay. Since it's negative, it's like a negative slope, so we know it's going to be this one. Okay. But when we talk about the arrows, we have to split this graph in half, and it's rising to the left, falling to the right. Just draw your arrows, you'll be okay. Saying it is harder than just writing it. Yes, you could just, yes, that's fine. All right. X-intercepts. Okay, so your zeros. So if we have x minus 1, what does x equal? 1. What's the multiplicity of it? 2. So is it going to cross through or bounce back? Bounce back. Okay, next parenthesis, x plus 2. X equals multiplicity. Bounce back, cross through. Cross through. Okay, so it's already factored for you. That step's really easy. But you have to do a little bit more work to find the y-intercept. Remember, y-intercept, we plug in 0. So f of 0 equals -2 times the quantity 0 minus 1 squared times 0 plus 2. What is 0 minus 1 squared? 1. And 0 plus 2? -2 times 1 times 2? -4. Okay, and then our last one is our symmetry. Okay, when it's in factored form, it's harder to see, but usually this will be none. Okay, and the reason why is because if you were to FOIL this, x minus 1 squared, you're going to get x squared minus 2x. So now you have an even and an odd. So it's neither. Okay. So usually when it's already factored, just know that your symmetry will be neither. Questions? Okay. So let's just leave our scale normal. So we have an x-intercept at 1. We We have an x-intercept at -2. And we have a y-intercept at -4. Okay. So, starting on the left-hand side, is your graph going to start above the x-axis or below? Above, because this is top arrow. Okay. And when we get to this x-intercept of -2, are we going to bounce back or cross through? Cross through. Okay, so we're going to cross through it. We know we're going to come down. We don't know how far, but we know we're going to have to come back up and go through that y-intercept. And then when you get to that next x-intercept, are we going to cross through or bounce back?
Bounce back.
Bounce back. And there's your graph. This section right here, that's what you don't know. You don't know how far your graph is going down. Just do your best. Okay? Just do your best. I'm not going to make you find x values and plug them in to figure out how low this goes. We're just sketching the graphs. Sound good? Okay. What would your domain be? What would your range be? -infinity to +infinity as well.